Hey guys, this is Travis Legleiter, Extension Lead Scientist at the University of Kentucky. And what I want to talk about today is broadcast nozzle selection for optimal herbicide applications. And when we typically talk to you guys about herbicide applications, the steps we take is first identifying which pest or which weed you're trying to control. Next, deciding what is the correct herbicide to control that weed or the best product to control that weed. And then applying that product at the correct size of weed. And then the last thing, and the thing that we don't always hit on the most, is how to deliver that product from the tank or from the boom to that target weed. And that's what I really kind of want to talk about today, is some of those parameters we have to think about when we're thinking about that delivery of that product. And so when we're talking about delivery of the droplet, it can be a very large challenge. So there's two destinations for those droplets. They can land on their intended target, which in a perfect world, 100% of them would, which we know is not reality. And they can also land off of their target, which, as we know, is something that we try and we want to avoid in all scenarios. They can also evaporate or become suspended in the air. And those droplets we don't have a lot of control of, but they will ultimately end up either on their target or off their target. And again, we don't have a lot of control of those droplets that ultimately end up doing that. But we can control a lot of our destinations to those droplets by picking the right nozzle design and droplet size, and those really do help us out quite a bit with that final destination. And so first of all, let's just talk a little bit about droplet size. So you guys are as an applicator, you're probably familiar with the different droplet size categories, such as medium, coarse, very coarse, extremely coarse, ultra coarse. You're used to those. You've seen those. They're usually color coded. And the reality is, or what I want to talk about here today, is your spray nozzle isn't just putting out one size of droplet. Yes, it's putting out that droplet category, but it's not just one size of droplet. It's putting out various sizes from small to big across that spectrum. And so when we measure our droplet size, what we're doing is we're measuring those droplets, we're measuring the diameter of the droplets in microns, and then we're measuring as many droplets as we can across that spray cloud or the spray volume coming out of that nozzle. And then we take the cumulative volume measurements. And those are things such as DV50 or VMD. You've probably seen those before. Also, some other things we can think about is DV10 and DV90. And I just want to show you a little bit of what that might look like. Now, this is a bell curve, and this is a nice, pretty, perfect bell curve, and this is not reality, but it's good for demonstration purposes. So within your spray plume or within your with what's coming out of your nozzle, you're going to have droplets in this case that are anywhere from just below 194 microns or little droplets up to 674 microns or big droplets. Okay. But the majority of them fall somewhere in here. As you can see, the majority are right in here within this bell curve. And that DV50 typically tells you where most of the droplets fall. And the DV50 essentially is what tells you is 50% of the droplets in this case are 434 microns or smaller. So that DV50, it gives you a pretty good idea where the majority of the droplets are as far as the size within that spray cloud or within that spray volume that's coming out of that nozzle. But the DV10 and the DV90, numbers that aren't always published, you don't see a whole lot, can also tell us a lot about that nozzle. And so the DV10, what this tells us is 10% of the droplets are this size or smaller. And the DV90 tells you 90% of the droplets are this size and smaller. And so what these can tell you is they can tell you a lot about where the majority of the droplets fall. Again, because again, this is a nice perfect bell curve, which is not reality. This bell curve could be skewed to the left, it could be skewed to the right, it could be more narrow, or it could be more broad. And that DV10 and that DV90 can help you in understanding that. The DV10 can also help you understand how many driftable fines you might have, because it's typically down there it's going to be on the lower end or the left side of that bell curve. So I just really wanted to point this out, that when you think about your droplet category, you're really sliding the bell curve up and down, and that's what you're doing with it. And the reality is, even though you're spraying a droplet category that's really big, there's still going to be a small percentage. It's not a lot, but there's still going to be a small percentage of droplets within that spray plume that are much smaller or potentially driftable fines. Okay, so that's just something to be aware of when you're thinking about your nozzle and your droplet size. The other thing to think about is before you go to select your nozzle is to think about what type of rate controller do I have? So the traditional types of rate controllers are what we've used for a long time, are pressure-based rate controllers. With these rate controllers, as we increase our speed in the field, the pressure increases on the system. And as we decrease our speed in the field, the pressure on the system decreases. And this keeps our spray volume the same across the entire field. Now, with these systems, as I'm getting ready to talk about with nozzle types, as you increase and decrease your pressure, you're also changing your droplet size. So across that field, you are continually changing your droplet size. Now, with the pulse width modulation system, this is a video of one of those systems, and you can see those nozzles very quickly pulsing, or the spray plume pulsing out. You can usually pick these out as they go through the field. It's a little bit more of a modern system, but they are available. They've been available for many years now, but many of our sprayers now have these. And with these, you select your pressure, or you set your pressure based on typically what size of droplet you want. You set that pressure, and then from there, as you speed up or slow down, the duty cycle, or the number of pulses that occur, change to keep that spray volume even across the field. So that's a really simple or simplified explanation of how it works, but that's about as much detail as we're going to go in today. And I'll explain to you why this is important as we get into these nozzle types. So talking about nozzle types, you're gonna hear some terms of different nozzle types, and I just want to talk through a few of those. So a single stage nozzle, these are often also called extended range nozzles, or ER or XR. You've probably seen that nomenclature. With these nozzles, what you have is a single orifice, and that one orifice has two jobs. The first is to meter the amount of product or give you the size of the nozzle. So for in this example, with this particular nozzle, you can see it's an 0.4 nozzle, so that gives you 0.4 gallons per minute at 40 PSI. So you guys know about that sizing. So that's the first job, is to give you that spray volume, or the amount of product that's coming out at a given pressure range. And the second job is to create that flat fan, or that tapered flat fan that we're all familiar with. With these types of nozzles, the reason why they are liked, or they're called extended range nozzles, is you can run them across a large pressure range, and as you run them across that large pressure range, they change their droplet size. So at higher pressures, they have smaller droplets, and as you decrease your pressure on these nozzles, you get big droplets. So it's an inverse relationship. And with herbicide applications, and especially if you're on a pressure-based rate controller, this can be problematic, because as you speed up and increase the pressure on that system, you're decreasing your droplet size, which may not be desirable. One way to overcome this is by using a two-stage nozzle. So a two-stage nozzle, essentially what we've done, these are also called pre-orifice nozzles, is we've taken those two jobs I talked about, and we split them apart into two different jobs, into two different orifices. So you have a pre-orifice, and its only job is to meter or give you the spray volume that you have. And then the exit orifice, all it does is creates that flat fan, or that tapered flat fan pattern. And so with these, they're not as prone to differences or changes in droplet size as we change our pressure. You can see here in this chart that they still do change their droplet size over different pressures, but they're not quite as prone to it as those single stage nozzles are. And overall, we can get a larger droplet spectrum out of these nozzles as compared to a single stage nozzle. Now, some of the original nozzles, they really only operated within a very narrow pressure range, but the newer nozzles and the more modern nozzles incorporate some type of spacing or gapping between the two orifices, which allow these to be ran over a pretty large pressure range. And these nozzles are really liked by a lot of applicators for that. Now, if a person's really wanting a very large droplet, or if your goal is to have some big droplets because you're trying to avoid something like drift, in those cases, you're probably going to want to go with an air induction nozzle. And the way an air induction nozzle works, typically, or these are always going to be a two-stage nozzle as well. So they'll have a pre-orifice and an exit orifice. But between those two orifices, you have air inlets that pull in air and mix the air with the spray mixture before it goes out that exit orifice. And you get these air-filled droplets, or these very large droplets that come out of that nozzle, ultimately because of that air induction technology. And so these are great nozzles, and often they are used, or they're promoted for their potential to produce very large droplets that are less prone to drift, right? The one thing I want to go back to is spray rate controllers here. If you have a pulse width modulation system, you more than likely aren't going to want to run an air induction nozzle. And the reason for that is that pulsing mechanism disrupts the air induction and the air induction feature just does not work well when you're using those pulses. And with those, you have to go back to a two-stage nozzle. But there's many two-stage nozzles out there, such as this, just one example, such as this DR nozzle, that do a very good job, that if you pick the right size of nozzle and put it at the right pressure, you can get very large droplets with these and put it on that pulse width modulation system and spray with a large droplet and keep that droplet size consistent across that entire field. So those are just a few things to think about when you're trying to select your nozzle, and kind of guide you towards which nozzle should you go for based on what size of droplet that you're ultimately wanting. And when you're trying to decide, well, what size droplet do I want, right? What you have to think about is balancing how much coverage do I want, how much deposition do I want, and how much do I want to mitigate my drift potential, right? You have to think about all of those things at once, and there's some additional factors here that we can think about on top of that, and we'll talk about all of those. I want to talk about drift first, okay? Because it's usually the first thing that comes to our mind, right? So we know that with droplet size, the bigger the droplet, the less likely it is to drift or move with wind or horizontal movements. This is nothing new. If we're trying to avoid drift, the best thing we can do is increase our droplet size, because that droplet is going to fall faster and it's less likely to move off target. And generally, any droplet that's below 200 microns, we're going to consider that a driftable fine, or a droplet that's really prone to drift or to move with the wind, even under ideal wind conditions. So those are the ones we're trying to avoid if we're trying to avoid a drift scenario. And this is what's within our control, right? But we can also use some other things that are outside of our control, but we can spray in the right environment that can also help us with drift. So spraying when winds are low. If the wind's over 10 miles an hour, we should really be thinking, should I be spraying or not? Avoiding situations where we have really high temperatures and really low humidities. In those situations, our droplets can evaporate, and as they evaporate, they get smaller and they're more likely to drift. Now, in the state of Kentucky, we don't really have to worry about this, but there are certainly places where we grow row crops throughout the United States where this is an issue, and you have to think about it. We also have to think about air inversions or temperature inversions, and these are things we've learned a lot about over the last couple of years, and we need to be aware that we cannot be spraying into those types of scenarios. So while you can't control the weather, you can work around it, and it's something to keep in mind when you're thinking about drift. The other thing that you can control that you really need to pay attention to is boom height. Our boom needs to be 18 to 24 inches off the target. Now, the reality is a lot of booms are 30, 36, 48 inches above the canopy or above the target. And the reason for that is it's really an applicator comfort thing, right? And with those big booms, it's really hard, or it's really difficult to keep those booms low because it's a comfort level thing, and we understand that. But when your boom's lower, that droplet spends less time in the state of fall, and it's less likely to move off target. Whereas if that boom's really high, it takes a long time for that droplet to find its target, and it's more likely to move off target. And we've shown this multiple times. So do everything you can to keep that boom down at 18 to 24 inches to help reduce the amount of drift that you have. So you've done all that. You've thought about, okay, what droplet size do I need to mitigate drift? But the other thing you have to think about is, well, I still need coverage. I still need to deliver this. And I need to think about how much coverage and how much deposition I get. And those are two different things. And that's what I want to point out here right now. Coverage and deposition, as the way I define them, are two different things. So coverage is something that we see such as on these spray cards. And I think we can all agree that this card right here has better coverage than this card. And this one falls right between the two of them. And so coverage is kind of it's a 2D measurement. We know that there's more coverage here than there is more coverage here, but that doesn't tell us what type of deposition or what volume we put onto that card, because we don't know the third dimension. For example, right here, we don't know the depth of that droplet or that blob that's sitting on that card. So we don't actually know if there's a difference in the amount of product that got deposited on this card versus this card. And so as we get into this, we'll talk about that a little bit more. But when you're thinking about, well, do I need deposition? Do I need coverage? Do I need both? Do I only need one? Things you need to think about are, what type of herbicide are you spraying? If you're spraying a systemic herbicide, something such as glyphosate or maybe 2,4-D or a dicamba, those are systemic products. Those are products that once they're placed on the plant, they're moved to the target site and they're moved throughout the plant. And with those, the most important thing is that we're getting good deposition, or the most deposition we can on those. And coverage, we can sacrifice a little bit because they are systemic. Whereas if it's a contact product, something such as paraquat or glufosinate or Liberty, with those, we have to have good coverage because they don't move in the plant. And so with those, coverage is essential. So with those, we want coverage and deposition. Some other things you have to think about is, what are you trying to target? You're trying to target the soil? Are you trying to target a grass or a broadleaf? What time of day is it? Are those plants moving their leaves up and down? And how much of a density or canopy do you have? What's your crop density? What's your weed density? We have to think about all of those things as well. And so when we think about those, let's talk about droplet size first and how droplet size influences deposition and coverage. So we know, and we've known this for a while, that the smaller the droplet, the better coverage we get. So in this example, these are the smallest droplet producing. This is a small droplet producing nozzle all the way up to a large droplet producing nozzle, if you will. And you get better coverage with this nozzle than you do this nozzle and everything in between as you move up. So we know this. We've known this for a while. If you're looking for coverage, reducing your droplet size can help you with coverage, and big droplet, those ultra coarse droplet producing nozzles are going to sacrifice coverage. But that doesn't mean that droplet size is going to influence your deposition, and that's what we've learned. In this scenario, we were spraying goosegrass, and with this TT nozzle produced a medium-sized droplet. This produced an extremely coarse droplet, and this nozzle produced an ultra-coarse droplet. So, if you will, from a small to a big droplet spectrum. And with all of these, we got the same amount of product deposited onto target goosegrass plants, regardless of our droplet size. So, even though we know we probably got better coverage here than we did here, what was being deposited was the same. And in this case, this was on water hemp. And this is the same thing. If you will, this is a smaller droplet producing nozzle up to a big droplet producing nozzle. And with each of these trials, so 2 different trials of water hemp here, in both cases, we kept the same amount of deposition on those plants, regardless of what type of nozzle or droplet size we were using, even though we know that we had better coverage with this nozzle than we did this nozzle. It does not correlate to deposition. And if you're using something like a glyphosate dicamba 2,4-D, deposition is what we really need. And in these cases, we can use these very large droplet producing nozzles and get us what we need. Now, if you're spraying a contact and you're concerned about coverage, rather than just saying, okay, I'm going to reduce my droplet size, one thing we can do is we can change our spray volume, right? So we can change our spray volume. So in this case, this is 10 gallons per acre, and this is 15 gallons per acre. And so with these, over 6 different scenarios, every single time we got better coverage with 15 gallons per acre than we did 10 gallons per acre. And again, this is something we've known for a while. So I'd encourage you, if you're really concerned about coverage, rather than saying, I'm just going to reduce my droplet size, let's think about spray volume first and thinking about maybe increasing our spray volume rather than reducing that droplet size, because we know spray volume affects coverage pretty significantly. Now, the last thing I want to hit here when we're talking about deposition and coverage is weed density and what influence that has on it. And it's something we've been looking at here. Okay, so this is one example where we had a trial of 3 different nozzles. So again, a medium droplet producing nozzle up to an ultra coarse droplet producing nozzle. And we applied those over 3 different densities of water hemp. So 6, 27, and 54 plants per quarter meter squared. And you can see here, we lost control when we're using that ultra coarse droplet producing nozzle. We lost control with that nozzle when we're spraying it on high density populations. But if we sprayed it on the low density population, we are able to get good control and equivalent control as compared to that medium droplet size producing nozzle. So what I'm trying to get at here is, again, if you're worried about control and using these large droplet producing nozzles, one key is not only getting your spray volume correct, but also making sure you're not spraying these high density populations. And if it's a post-emerge application, the best way to overcome that is use a pre-emerge herbicide, and it'll put you in a scenario where you're spraying these smaller densities and allows you to use some of these larger droplet producing nozzles. So taking that all into mind, and that's a lot of information, but taking that all and wrapping it together, when we're trying to maximize that droplet for a herbicide delivery, we really do have to balance mitigating our drift, but also achieving the coverage and deposition we need to make that given product work. But we can use, and those 3 don't always work together, but we can use things such as spray volume or weed density or boom height or environmental conditions to help us out and help us get that balance. So it's a lot to think about and a lot to keep together, but we can achieve this, and we know we can achieve this. With that, I want to thank you guys for joining me today. Here's my contact information. Feel free to email me in time, follow me on Twitter, and thank you for joining me today.